Hey, everybody. Welcome to the second lecture of data science or econometrics for data science. I'm going to start out today, this morning for me, but maybe not this morning for you. So let's look at this is my last collab notes. And I'm going to just go over the quiz. Again, one thing I want to remind you of is the quizzes are hard and some people did a great job. Some people struggled a little bit. That is fine. That is expected. This one in particularly, you kind of learned how these quizzes will work. You now know they're going to be a little bit tricky. I don't want you to worry about your grade on this particular quiz. We will not let that ruin your outcome in the class or anything like that. So I'm going to quickly just go over the questions and see how we might have answered them. So these ones are very directly related to the video I showed. After the demand curve shift shown in the video, so let's go find that. Here's a demand curve. Here's a demand curve shift. Here's $10. That was the price before the shift. So here we see that the price is higher after the shift. So that's why this one was more than $10. If the cost of producing ice cream increases, that means the supply is going to shift in. That's one of the shift reasons. In a heat wave, people want more ice cream. So the demand curve shifts out. So this is an outward shift in the demand curve. Now, at the same time, the production cost thing is going to cause the red curve to go to the left, this direction. And so that means we're going to be somewhere up here on this demand curve for our new equilibrium. So definitely price will be higher. It's not clear what will happen to quantity because it's possible that quantity will be higher from the heat wave or that quantity will ultimately be lower depending how much the supply curve shifts. And here's an example of the supply curve shifting to the left. So both of those shifts happening at the same time is what's being described here. Price will definitely increase. It's not clear what will happen to quantity. In order to estimate the slope of the demand curve, we need to hold the demand curve constant. That was one of the big lessons of the day. So here's neither supply nor demand being held constant. And then we get this nonsensical slope. Here's actually an example where we held demand constant and just shifted the supply curve. So that's a big lesson. If you don't understand that one, make sure to talk to me or make sure to think about it. And if you don't get there, please ask me about that one because that's big. Now, if both the supply and demand curve are shifting outward to the right at the same rate, then we're probably going to get too flat of a demand curve estimate. So we can kind of think about that. I would draw that out. That would be a good one to put on splash paper. Like do an original demand and supply, then shift both of them to the right, then shift both of them to the right again. You're going to get a bunch. If you did it like perfect shifts, you literally get a horizontal line instead of a downward sloping line. Or sorry, an upward sloping line because we're talking about the supply curve here. That's why it's too small. That's why I had a weird little break, mind fart there. If only the demand curve is shifting and the resulting equilibrium points are used to estimate the slope of the demand curve, the slope is likely to be positive because really you're more likely to get a slope of the supply curve in that case. And the law of supply says that that is a positive slope. All right, so there's the quiz recap. Today's lesson is the linear regression model. Right off the bat, so there's some announcements. That's kind of the quiz thing. Oh, I've promised a couple of you in meetings. Thanks for doing the meetings. I have a couple meetings upcoming with you still. I will post the actual dates. In the last video, I told you the dates right now are placeholders for the poster session. I will put the actual dates for that as soon as possible. I do have them. It's more a matter of me not remembering to put them in there but I do have the dates. I think it'll be like December 2nd, but approximately the dates in there are when you should be thinking about being ready for it, but I'll get those in there soon. So let's talk about the linear regression model, or specifically the multiple linear regression model, because at this stage, we will often be dealing with many independent variables or more than one independent variables. I assume that a lot of you have seen linear regression before. maybe not in matrix form, which is we're gonna look at that today. Um, but yeah, I just want to like to motivate it. I mean, the linear regression model forms the basis for many of these very powerful things that we see. In particular, neural networks are a huge one, the basis of AI. So I said, I was wondering if am I lying to them? Does linear regression actually form the basis for neural networks? I was pretty sure it did, but then I just decided to Google this to double check right before this video. And even AI, Gemini, the neural network says yes. Neural networks fundamentally build upon the concepts of regression. So, boom, this is good, powerful stuff. Here's a Medium article by this guy. Neural network is nothing but a linear regression. So, boom, there, it's important. Some people are like, look, regression is the old thing. Now I use AI. So now we know they don't know what they're talking about. So, let's get into it then, because clearly I've proved beyond a reasonable doubt that it's important. The multiple linear regression model forms the basis for many statistical and machine learning methods. So this is kind of the most basic version, right? This is a population linear regression. I know that because I have Greek letters right here, which we'll talk about. Y, our dependent variable, or potentially a set of different dependent variables, is beta. So that's going to be an intercept or a constant term because it's not being multiplied by an independent variable. Beta 1 is x1, whatever our first x variable's slope is. And so beta 1 is the population slope. It's a beta. We don't believe that when we're setting up these linear regression population models that they are perfect. So we always include an error term, and there's some special characteristics about that error term that we'll talk about a little bit today, but throughout the course. So we might refer to these, I called it the slope just now, but it's also called the weight. For in a neural network, it's usually called the weight or a coefficient or a slope. Those are all acceptable and reasonable. There's probably more. We could also pack all of the independent variables into a matrix and write the model as this way. Notice now we only have n1x right here, and it's not labeled. And then we could just define each of those vectors and matrices. Of course, y is just a vector of y individual. So this is like the first dependent variable observation in our population, maybe. First independent variable observation in our data. In this independent matrix, we include these ones to make sure we get this intercept in there. If we don't include those ones, then we wouldn't have an intercept or a constant term in the model. You will show that these things are equal in the homework. It is important to distinguish between a model and the estimation of the model. And that's a very important thing in econometrics. That gets muddled, I think, a lot in computer science and more statistical applications. Econometricians focus on this part a lot. We really care about the underlying model before the estimation. I would say that's one differentiating factor of econometrics is we focus a lot more on what's going on before we start doing estimation. That's why this distinguishes modeling is sort of what happens before I estimate. Estimation is happening while I estimate. Okay, I think that distinction will be clear though as we move forward too. So suppose I'd like to estimate the impact of the years of education on unemployment, and I have panel data. So we'll talk about different types of data in this class. Panel data means time is changing. So we have a time series component and space is changing. So maybe I'm tracking 100 students, 2 in every state, and I'm getting data from them once a year. So that's panel data because they're in every state. So they're spread out geographically, spatially, but I'm also like observing them over the passage of time. That would be panel data or longitudinal data. So I don't know why I made up new numbers when I said it, but 1,000 people every year for 10 years, same thing. So that's a simple linear regression model we might look at. It's a simple linear regression because there's only one independent variable. Note here too, I've written the model in a new way. So here I have vectors, here I have matrices, here I have the definitions of those matrices, here I have the individual observation or arbitrary observation formulation, IT in time period I, or sorry, individual I in time period t. So this is a linear regression model, but we've made no statements about how this model will be estimated. So we can write this model down. We're doing modeling, but we have not said anything so far about estimation, and we could estimate this a lot of different ways. Note that we could say in this individual observation setup, each individual I has survey responses associated with time t. For example, if the 242nd observation survey respondent had an income of 37,450 in 2007-3 when they had 14 years of education, we could write income 242 because they're the just like if assuming they're the 242nd person in the data set. 2003 equals there's their income, there's their years of education. So that's just what individual observations might look like in that context. Note at this point, we are making assumptions and hypotheses about the population because we haven't really talked about sampling yet. So when we move into estimation, we'll take samples in order to estimate the population parameters like these betas. But we haven't made that transition as of yet. Right now, we're just going to do a little simulation to show the population. You should think of this as a population scatter diagram because we haven't said anything about taking a random sample of individuals or anything like that. So this is just what that graphically looks like, is that we have a straight line because it's a linear regression and just one independent and one dependent variable. And then, of course, the blue dots, the observed data, we have errors. So just reiterating that we do not believe this is going to be a perfect linear relationship, but on average, the relationship between years of education and income can be well described maybe by this, in this case, an upward sloping relationship. But absolutely, we're going to allow for errors around that, and that is fundamental. So now just the reason I'm doing this is I want to give you an idea of what these guys might look like, because we showed this is the matrix form. These are all matrices. And now we can go look at, okay, so income, here's our income vector. So we could say that's just a vector because it's just a column of numbers, and those look like reasonable incomes other than the crazy decimal points. Here's our intercept because we have that column of ones just like we did above. Here's our years of education. And now we have our coefficients. Notice there's only two coefficients because we have the one for the intercept and the one for the slope. And then, of course, we have the error terms. So that's just what this is obviously arbitrary, but then we made a simulated little population regression and we can actually look at what those matrices would look like in this. And you could do the math to show that this guy plus this times this plus this error equals this number. Like that's how the math, and you're going to show that with variables on the homework. Oh, by the way, on showing it with the variables, notice if we double click in here, we can do some pretty nice math writing. So this is where I've written my matrix. You can totally copy that because if you make a copy of this notebook, you'll have access to that just to give yourself, so you don't have to like start from scratch and writing the math nicely. And I would like you to try to write the math nicely. So there's our slope interpretations are extremely important. How many times I've had somebody who's like basically a super genius PhD in math and computer science and data science and everything else not be able to interpret a slope of a simple linear regression is insane. And so you need to be able to do that. It's unbelievable because I think people's careers get messed up because they're like so good at math and computer science and data science, but then they like can't even tell any client who's not going to be super good at those things what the numbers mean. And so that's why it's super, super important. And I will emphasize it at your poster. I will sneak in some type of slope interpretation, and yours probably will be much more complicated than this. So you need to practice it and think about it. There are many instances of analysts applying extremely complicated machine learning techniques to estimate slopes, but then being unable to interpret the estimates in a meaningful way. Beta I, so the coefficient on xi, like beta 1 is the coefficient or slope on x1. Is the rate of change of y the dependent variable with respect to xi? Since we are considering a linear model, this rate of change is constant. So we can say things like when x increases by 1, y increases by beta. If we have multiple independent variables, then we need to say when x increases by 1, y increases by beta, holding the other independent variables constant. And they might be, those independent variables might be correlated with one another. So that becomes a more important and maybe a less meaningful. So more important in terms of saying something correctly, but maybe less meaningful in terms of how reality works. Like if two variables always move together and you say holding this one constant. So a big one is holding square footage constant, increasing the number of bedrooms in a home will decrease the price of the home. So that's a little bit weird because normally we'd expect a positive relationship between number of bedrooms and home price, which is true on average in the data if you don't hold square footage constant. Think about that example. It's the one I always use because I think that one is good to really understand the nature of these types of interpretations. So for the education example, we made up the slope of 5,000. We'd say when years of education increases by 1, salary increases by 5,000 on average in our data, because that wouldn't necessarily be true for individuals who have error terms, right? Note that since we rarely directly observe slopes because it's a population parameter and we will estimate it, that's when we say on average in our data. So maybe I can like hedge a little bit on that 5,000 since we pretended we knew the population parameter. So now that's really the bread and butter. What are we doing? We're trying to set up linear models where we have one independent variable in general, but we could stack several equations into a model like this with more than one and multiple independent variables. Most likely we're working with a multiple regression, although simple regressions are common and important to this day too, depending on the question we're trying to answer. So this is just a graphical idea of the same thing. Here is just what the numbers look like in the matrix form. Interpreting slopes is very important. So now I want to go through some different types of variables that we might encounter. And this becomes a huge thing in data science because data science is a place where you really will encounter all different types of variables. So the most common and simple that we've already dealt with in this video are continuous variables like income, or height is a continuous variable, or temperature. So they just continuously measurement. Like imagine I'm using a ruler to measure this thing, or I'm using a scale. So those are continuous variables. I won't spend too much on time on that because I assume you know about that. Categorical variables, things take a limited and fixed number of possible values. So things like labels or names. So marital status might be single, married, divorced, blood type, I said A, comma, B, AB, O. We generally code non-ordinal variables as 0, 1. So that's like yes or no. Non-ordinal, you can think of it like, is your blood type A? Yes. Then it would be 1 because you are 1 for yes. But it wouldn't be, we wouldn't probably want to do something like, let's make A0, B1, AB2, O3. Why wouldn't we want to do that? Because that's ranking, providing order where none exists. So that would be a problem. If we had blood types being important in our analysis, we'd want one variable called type A, 0 if no, 1 if yes. Another variable called type B, 0 if no, 1 is yes. You probably already know that, but those are things worth critically thinking about. Another big mistake, people that are very good at math and computer science, not thinking about these more simple things like, does it make sense to put blood types in order? And you definitely should be thinking about that because people won't believe you're good at math or computer science anymore if you put blood types in order. You can crush a lot of hard work with simple things like that. And that's one of the things about this class. Be detail oriented on the front end when you're making the model. We generally code I already told you that. Ordinal variables. So ordinal variables are categorical variables, but there might be an order involved, like education, high school, bachelor's, master's, PhD. Also, probably a mistake to do 0, 1, 2, 3, 4. Because now we're thinking like as one variable called education, because now we're saying that there's like a similar gap between those in our measurement of them. So even with that ordinal, you probably want dummy variables like 0, 1s. Satisfaction level, very unsatisfied, neutral, satisfied, very satisfied. Another one that's really common, actually, that you might appreciate is student evaluations are like this. So, like, not exactly these words, but words like that. And dude, data people will use like pretend that, I mean, it is ordinal. But the issue comes in when you make a variable that's like 0, 1, 2, 3, or 4, because 0 and 1, 1 to 2 are the same distance in that new scale that's getting put on top of these things. That can be a huge mistake statistically. So, another thing to be very careful about. Binary variables are a special case of categorical variables where they can only take two values. So like like yes or no questions is the best way to think about that. Almost always we'll do yes is 1, 0 is no, unless there's something really special and weird going on where that's problematic. So really quickly, because we just went over slope interpretations, we could say when blood type A increases by 1, cholesterol increases by slope. That would be weird because blood type A is a variable that is yes or no, and it's 0 or 1. So it's kind of weird to say when it increases by 1. So with those types of interpretations, it's more sensible and I mean, it's true to say when blood type goes up by 1. It just doesn't really like we wouldn't speak in that way normally. So a better interpretation there would be like on average in my data, holding other variables constant, people with type A blood have X different or beta different cholesterol on average than people without blood type A in my sample. Now, if we just put 1, 0, 1 variable in a regression, like here's our simple regression. Imagine if this was a 0, 1 variable. Now, the interpretation I just made, combined with that idea that we could do a simpler regression with one variable, and then the interpretation of that variable that I just made is beta 1 different than the average if it's a 0, 1. That means that if we're doing binomial variables, that a simple linear regression is the same thing as calculating the difference in means between two variables. And you will prove that in the homework. Good job. Good job in the future to your future self, proving that in the homework. It's not that complicated, and it's good to know because that tells us something important. Now that we have regression, we can look at difference in means, and then we could add other control variables and control for other things that we might lead to those difference in means other than our key binomial variable. And that can be very important in trying to figure out the truth about different phenomena in reality. So now I'm just going to look at some graphs about like what are these, because this is continuous. That's going to be kind of the more straightforward one. Although years of education was just an integer, but we'll imagine we could have put 14.5 in or whatever. So let's look if we just had pure categorical. What's going on here? No degree 0, bachelor's degree 1. This is what a scatter plot of that would look like, right? Because the independent only takes values of 0 or 1, but we could still do a regression and it would still be meaningful. Those are nice sometimes. We can think about this looks like it has more variation around this mean than this. Things like that are interesting. Here's binomial outcome. Some people don't like this. There's a lot of debate about whether you should do what is called a linear probability model. That's what we're looking at right now. That's if you just run a simple regression on a 0, 1 outcome. Machine learning types tend to hate this, but not for necessarily the best reasons. So other ways to do this are with things like logistics or logit regressions or probit regressions. That forces the red line to never go above 1 or below 0 because those are impossible values, but other things change. And that's a trade-off, which we think about in economics a lot. that naturally leads to maybe some other issues with estimation. So it's not a pure benefit to switch from a linear probability model like this to a probit or a logit or some other words that you machine learning types use for those two. Now we could have all binomial variables. This is 0, 1, and 0, 1. So 0, 1 independent, 0, 1 outcome. So what's really the only reason this has a slope is there's more density packed into this guy and or this guy that's pulling the line like that than in the others. And so you can still get, even though all the points are stacked on top of each other because it's all zeros and one combinations, we can still see and estimate relationships there. Now we're doing linear regression models and we can do nonlinear regression. Some people get super into nonlinear regression, but I feel like they're guided for the wrong reasons. Like, oh, nonlinear sounds better. So let's do that. Neural networks, like I said, are built on the basis of linear regressions because we're getting so local and zooming in so much that nonlinearities tend to not be super helpful for us. We will, I think, talk about a little bit about nonlinear regression. But first, another mistake people make is that how many nonlinearities are already encompassed in linear regression is something like people will often deviate to nonlinear before they even understand that. It's like, well, you could have just done this with a linear regression that maybe has some better characteristics for you anyway, in terms of computational power required for estimation, things like that. So we can do nonlinear transformations. And so we'll just go through some examples and maintain the linearity of the regression. So notice here we have y, the dependent variable, and we have the arbitrary. Now we're just looking at cross-sectional data because I just have an I, no time series component there. yi, the dependent variable, equals an intercept plus a slope, now times the log of x. So we can transform our x variable in a nonlinear way, and then it can enter the linear regression, and it is entering that linearly after a nonlinear transformation. So we can do a lot with that because we can always make nonlinear transformations before this. So really what nonlinear and linear comes down to is more about additive separability oftentimes than it is about nonlinearities per se. So slope interpretation, we expect y to increase by beta 1 over 100 for each 1% increase, because now, of course, we have to get a little bit more careful about slope interpretations, right? This interpretation works for small changes in x. For larger changes, we'd say yi increases by beta 1 times log percent change in x. For example, a 10% increase in x leads to a beta 1 log 1.1 change in y on average. So we have to be careful, obviously, with slope interpretations once we wrap independent variables and nonlinearities. Now, log linear transformation. Suppose we believe stock price grows at a constant percentage rate over time on average, but with error. So this is literally a stock pricing and commodity pricing formula that is very common. So where PT is the price of stock at time T, P naught is the stock of price at T0. So the initial price of the stock, and R is the growth rate. Now we can just take logs of that. This is a linear regression now that we've taken logs. Now that's linear. So we can often transform nonlinear looking regressions or equations into linear regression models. Another one, so we could write literally, now we're just transforming into our language with betas, and then we can get those interesting parameters from a price growth model from that regression. Log transformations. Sorry, I'm obsessed. There's other ones, but sometimes I'll randomly be like, I'm going to fix this typo now. And so I did it that time specifically. Log transformations. These ones are very nice, very common in economics because we talk about something called elasticity a lot, which you can estimate this way. So the price elasticity of demand is an important quantity in economics. It is the quotient of, whoa, that's a crazy typo. So it is the quotient of, approximately spelled right now. It is a quotient of the percentage change in quantity over the percentage change in price. So if we ran this regression, that's what beta 1 would be. It would be the percentage change in quantity over the percentage change in price. So we could say something like if the price goes up by 1%, the quantity decreases, presumably because of the law of demand, by beta 1%, right? Decreases by the law of demand because quantity demanded should decrease if price goes up, from the last slides, from the last video lecture. Polynomial transformations. So we can, just like we can take logs of independent variables, we might put polynomial transformations of independent variables in, and now we can have a non-linear, have sales be non-linear and ad budget. If my ad budget is 0, maybe I can pump sales a lot by increasing it a little bit. But maybe if I'm already spending a ton of money on ads, that I don't get as much return for additional dollars, this would be a great model if you believed ad spending, advertisement spending worked that way. So interaction terms are going to be really important in this class, especially when we get into things like difference and differences, but broadly important. So now, instead of just looking at independent variables on their own, we might interact them together and think about them together. So let's consider example of gasoline prices by state. So gasoline price gasoline price in state S at time t probably depends on oil price in state S at time t, because that's the main input. A refinery takes oil and makes gasoline with it. So oil is more expensive. The refinery has to pay more. Gasoline is going to be more expensive. That varies by state because California oil is more expensive. They have to import it on the ocean versus Texas. Oil is produced right there. So that varies by state. Now, California maybe is really different because it has higher taxes. It only can get its oil by the sea and stuff like that. It also has really hardcore refining regulations. So maybe I have to shift up the gasoline price in California by having a intercept. Like this is going to be a new intercept term because this is a 0-1 variable. Is this observation in California? 1, yes, 0, no. So this is just adjusting. I'm allowing the entire line essentially to shift up the gasoline price or down if I'm in California. Probably up because we just hear California gas prices are high. Now, also, maybe because of some of those regulations, that doesn't just shift it up on average. Maybe that changes the relationship between oil prices and gas prices, specifically in California. So I can actually interact my 0-1 California variable with my continuous, or really any other variable, oil price variable. And that's going to allow me, this is going to allow California to have its own intercept term because this is going to add or subtract from the intercept term. This is going to allow California to have its own slope term on oil price. And we'll see that algebraically now. So let's pretend, just for the sake of this, I'm only going to collect data from Utah and California to make this easy to think about. Then I could actually rewrite this regression model in 2 different ways. One is the Utah equation, where the value of California, that variable, is 0. So what happens to this equation if the value of the California variable is 0? Well, I just get this back. Gasoline price, notice I can write Utah there. Beta 1, or sorry, beta not, because that's not getting multiplied by California. Beta 1 also not getting multiplied by California. And then all of this is 0, that goes away. This is 0, so all this goes away. And then I get this simplified version of the equation. Okay. Okay, now what if I'm just looking at the data from California? Then California is going to be 1. So this is a 1. This is a 1. And then I can combine like terms and I see explicitly what I said before. Beta 2 just adds or subtracts from the intercept, depending on if it's positive or negative. There's the beta 2. And that's what I said it would do. It'll shift it up, add or subtract from the, or down, add or subtract from the intercept. Beta 3 right here allows the slope to be different in California. Okay. So that's what these look like. So here is so we might collect data, color it by state. And if we saw the yellow points and the blue points, we'd say, yeah, that's the model I need. Because I think definitely the intercepts are different. And we can see here that the slopes are different and you can test it. We haven't gotten into statistical inference yet, but this is something that we would be able to test. And so we can see also what would happen if we sort of ignored some of these things. And we can do this in the data. So this is essentially the same model, except now I'm forcing them to have the same slope or the same slope, but not a different and a different intercept. And now we can see what would happen if we didn't use the categorical variable. So now we can kind of think what would happen. Well, we would get our slope would be fine if the slope was the same in both of the states, if we ignore the intercept issue. However, that slope is not going to be fine in all cases. So notice that we have nice distribution. So I misspoke. The reason that the slope of the green line is approximately correct in this case is we have nice spread across oil prices across both states. So we get nice observations and the slope is the same. Now, if we go down here, look what can happen. Like even now, the slope is the same in the within the blue and within the yellow. But if we didn't adjust for the intercept, we'd get too big of a slope because of that spread on the independent variable side. And that's going to pull our green line. So we can get a bad slope by not controlling. This is a very important example in economics and econometrics. That's another one of those things that's often ignored. And it depends on what your goals are if it's a problem to ignore this. If we were to say the slope of the green line represents the slope between oil and gas, we would be wrong. It's too steep. And the reason we would be wrong is because of missing a variable bias. We have not included the important information that this data comes from two different states, Utah and California. Not only that, but California is apparently correlated with higher oil prices and higher gasoline prices. The fact that we're missing a variable that is correlated with both the independent and dependent means that we're going to get an incorrect slope, and that's missing variable bias. That's one of those things to really bring it back to the goal of today's. Econometricians think more about, spend more time thinking about the modeling. So where are we? Somewhere in here, I told you guys that to econometricians, we focus more on the model, what's going in before we start estimating. And this is an exact example at the end. Missing variable biases, you actually have to critically think. You can check later, but you're going to have to come think about all of the things that might be correlated with both of these variable and thus will mess up your answers if you don't include them in your model. And that's an example of thinking on the front end, on the model I'm using before I go down the rabbit hole of estimation, which we will do essentially next in this class, but always we'll have this special focus on modeling. All right. So don't hesitate to reach out to me if you have any questions. And I look forward to meeting some of you who I haven't met yet soon. And yep, I will see you soon. Bye-bye.